Hello, this is Dr. Mode and welcome to chemistry class today. Today we're going to start section 5 in chapter 15, and the first part is on entropy. Our scripture verse for today comes from Genesis chapter 1, verse 28. And God blessed them, and God said to them, Be fruitful and multiply, and fill the earth and subdue it, and have dominion over the fish of the sea, and over the birds of the heavens, and over every living thing that moves on the earth. So here's where we are in chapter 15. As you can see, we've finished sections 1 through 4, and we're on section 5. We're going to do part A today, and then part B will be where we start up next week, followed by the test. So there are two essential questions from this section. The first one is, what is the difference between spontaneous and non-spontaneous processes? The second is, how do changes in entropy and free energy determine the spontaneity of chemical reactions and other processes? So here is an example of a spontaneous process. So in the picture on the left, you can see an old rusty ship. So the process of rusting is given here in this equation. We have 4 irons plus 3 oxygen molecules go to form iron oxide. And as you can see, this delta H is a negative number, which means that this is an exothermic reaction. We have 1,625 kilojoules released during this reaction. So a spontaneous process is a change that once begun occurs with no outside intervention. So rusting is an example of this, and actually if you look at the picture on the right, the exact same process, the exact same reaction is used in hand warmers. These little packets are hand warmers, and what they're filled with is iron metal that once it gets exposed to air, the oxygen in the air, it begins to rust, and that energy, that heat that's released during that rusting reaction is what heats up these hand warmers. So what is entropy? Well, entropy, which is symbolized by the letter S, capital S, the entropy of an object is a measure of the amount of energy which is unavailable to do work. Entropy is also a measure of the number of possible arrangements of the atoms in a system that they can have, and in a sense, entropy is a measure of uncertainty or randomness. So the higher randomness or disorder, the higher the entropy. So this is related to the second law of thermodynamics. So the second law of thermodynamics summarizes the tendency towards disorder. The second law of thermodynamics says that when energy changes from one form to another, or matter moves freely, entropy, which is disorder, in a closed system increases. So there are some things that we can do to predict the change in entropy, and we're going to get to those on the next slide, but what does that mean? So if we look at the change in entropy of a system, and let's say we're going to look at a chemical reaction, or maybe even a phase change, a physical change, what we're going to do is we're going to compare the products and the reactants, or the before and after states. So if we take the entropy of the products and subtract the entropy of the reactants, we're going to get the delta S of the system. So when delta S is positive, entropy increases. So that means that when the chemical reaction occurs or the phase change occurs, there's more disorder when delta S is positive. And when delta S is negative, entropy decreases. That means there's less disorder. Okay, so this table that we're going to put together here is basically going to summarize the way that we can predict what happens with entropy. Okay, whether things increase in order or decrease in order. Okay, so the first thing is a phase change from a liquid to a gas. So if you think about the molecules, where are they more free to move around wherever they want? Where are they just more random, more disordered? Well, it's in the gas state. So when we go from the liquid state to the gas state, then delta S, the entropy, is a positive number, and we've increased the disorder. Now this also occurs when we go from a solid to a liquid. There's more freedom for the molecules to move around in a liquid, so that's where delta S is positive as well. So if both of these are positive, if we reverse these and go from a gas to a liquid or a liquid to a solid, then we should increase the order and have a negative delta S. Okay, so the next thing we're going to think about is what happens if we have a gas that ends up getting dissolved in a liquid. Okay, well, when that happens, you have something in a state where it's very free and disordered that goes into a more confined state that's got more order. So we've increased the order, which means we have a negative entropy, negative change in entropy. So if we reverse this, we end up with some gas that's trapped in the aqueous state that gets released back into the gas state. Then what we've done is we've increased the disorder and we have a positive delta S. Okay, now in this example, notice that we have a little reaction, and in this reaction, everything is in the gas state. So when we have this situation where everything's in the gas state, we can analyze it and look and see what happens. Well, we have a decomposition where we have one gas molecule that decomposes into two different gas molecules. Well, what we've done here is increased the number of particles here, and this increases the disorder. So in this situation, we have a positive delta S. Now, if we have another type of reaction where we have two gas molecules that react to form just one gas molecule, so this is a synthesis reaction, this will increase the order, okay, and we end up having a negative delta S for this reaction. Okay, now what we're looking at is the dissolving of salt. Okay, when salt dissolves to form sodium ions and chloride ions, this increases the disorder. It's going from the solid to the aqueous state. Okay, and now we have more particles that are more free, so it's more disordered, and we have a positive delta S. So if we have the opposite occur, like if we have a reaction where silver ions and chloride ions in solution react with one another, then they will precipitate out as silver chloride. Well, this increases the order, and we have a negative delta S. Okay, so the next thing we're going to look at is how temperature changes this thing. So if we have an increase in temperature, then we're putting more energy into the system. We have particles that can move around more freely, and we increase the disorder with an increase in temperature. And then we decrease the disorder, or we increase order if we decrease the temperature.